Hi, I'm Mr. Miller, and this is a lesson about understanding logarithms. So before we begin with that, here are some important considerations before diving into the logarithms part of this lesson. So first of all, there's an important concept, which is the concept of inverse. So I've described this before as you've got a doing and an undoing function. So for example, if you've got a function that doubles something, 2 times x, x being your input, so multiplying it by 2, then the undoing function is dividing by 2. So let's look at what happens with a number when we use that as input. So for instance, if we evaluate f at 6, so again, we're using as input, we're using 6 as the input, and if we multiply it by 2, we get 12. Notice that when we take that 12 and we do the inverse to it, divide it by 2, we get 6. So doubling 6 yields 12. And then it's undone by dividing by 2, you get 6 back. Now, I could have alternatively switched those two functions, so made the original function, the doing function, dividing by 2, and made the inverse multiplying by 2. You'd notice the same kind of thing happening. And what I mean is that when you divide 6 by 2, you get 3, and then when you take the 3 and you multiply by 2, you get 6 back. So notice that what gets done gets undone by the inverse. And as a result, we get back what we began, the number that we began with. So we could have lots of other examples. If a doing function was adding 1, then the undoing function would be subtracting 1. And now the one that's important for this unit is looking at, a numerical example of that. Adding 1 to 6, for example, gives us 7, and then subtracting 1 from that result takes you back to 6. So now on to what's important for this unit, looking at the exponential function, so such as 3 to the x. If this is the doing function, so we take a number and we do 3 to that number, then the undoing function is log base 3 of x, and we'll get to understand that more as we go. But here's a numerical example of that. So if I use 2, and what I do to the 2 is I go 3 to that 2 and I get 9. Now if I take that and I plug that into the logarithm, and I do log base 3 of 9, I get back the 2, which is the number I began with. So basically, here's what we're looking at. It's when we're doing logarithms, it's kind of like solving this equation. And you should be familiar with this. This is an exponential equation. You can solve this even without a calculator. If you recognize that 8 is a power of 2, you say 8 is 2 cubed, then obviously the x is 3. So this is the equivalent to doing log base 2 of 8. That also gives you 3. So if you're given a logarithm to calculate, you can just rewrite it in exponential form, and it will help you to figure it out. So if everything else was cleared off here, and all you were given was this log base 2 of 8, and you're saying, what is the result of doing log base 2 of 8? You'd say, well, I don't know what this is, but I know it should be the exponent, so that when I do 2 to that exponent, I get 8. So exponents and logs are really closely tied together, and it's really important that you know your powers to be able to do some things even without a calculator. So the second important piece here before we get into the lesson on logarithms is to know your powers. So I'm not talking about Austin powers. That's not the powers we're talking about. I'm actually talking about repeatedly multiplying numbers. Baby. Yeah. Sorry, Austin, you're not the powers we're talking about. Anyways, so we're talking about knowing your powers. So for instance, powers of 1. When you do 1 to the 0, 1 to the 1, 1 squared, 1 cubed, we always get a result of 1. And this is pretty straightforward. Everybody should know all of those. Do you know your powers of 2? It's helpful to know lots of powers of 2. So here are a bunch. I usually make students write these out on the boards even from the time they're in grade 8 even. Repeatedly multiply by 2, see what you get. And it's good to start memorizing some of these because it makes coming up with answers to things very easy to do if you know lots of the powers. So most people know anything to the 0 is equal to 1, provided the base is not 0 itself. Raising to the power of 1 is the base itself. 2 squared means 2 times 2, which is 4. 2 cubed means 2 times 2 times 2, which is 8. And so most people know, double it, you get 16, double it, you get 32, double it, you get 64, double it, you get 128, double it, you get 256, double that, you get 512, and double that, you get 1024. Some people refer to these numbers as being like memory numbers because when you look at memory storage devices, they tend to go up in increments of powers of 2. So if you have 1 megabyte of storage, doubling that's 2 megabytes, 4 megabytes, 8 megabytes, or gigabytes if you're not into small storage devices. But anyways, lots of people get familiar with these numbers. I remember when I got my first iPhone, it was an 8 gigabyte memory iPhone. I think the next one I got was 32 gigabytes, and currently I have one that's 128 gigabytes. It's nearly as much storage as I have on my computer. Right now my computer has 256 gigabytes of storage on it. Some people who are doing lots of work with pictures and videos get computers with even more storage, like 512 gigabytes or a terabyte of storage, which is a whole heck of a lot of room. Anyways, those are the powers of 2, and I'm just giving you a way that you can remember them. The powers of 2 are kind of like memory amounts. So powers of 3 go like this. Of course, everyone's going to know the first one, 3 to the 0 is 1, 3 to the 1 is 3. Everybody should know the 3 squared, 3 cubed, so just multiplying by another factor of 3, you get 27. 3 to the 4 is 81. I like to the exponent 4 because it's like squared squared. So 3 squared is 9, and 9 squared is 81. There's a quick way to get to the exponent 4. And knowing one more wouldn't hurt. 3 to the 5 is 243. Of course, you should be able to do a few powers of 4 as well. And powers in between are even good to know, and going backwards. So you should know by now that 4 to the power of 1/2 means the square root of. And negative exponents means you do 1 over same base to the positive exponent. 1 over 4 squared is 1/16. And so on. So you can go in many different directions with this. You should know some powers of 5. So again, I like to go up to the exponent 4 because it's like 5 squared squared. 5 squared is 25. 25 times 25 is 625. So that's a good one to know. And it's also good to know at the very least your perfect squares up to, I would say, at least 20 squared. So here they are. And what you can do to make sure that you start remembering some of these things is either recite them orally or write them down either on a scrap piece of paper or on a whiteboard. For me, what I found when I was studying is if I had a test coming up and I needed to have something memorized, I would write it out 6 times. And if I wrote it out 6 times, I would own that thing that I needed to memorize. So I'm going to recite these out loud. You can feel free to recite them with me or just write them down as practice. 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100. Powers of 10 are really easy because the exponent is always equal to the number of zeros. So like 10 cubed would be 1,000. It has 3 zeros in it. Moving on to 11. 11 squared is 121. 12 squared is 144. Now, elementary school students have memorized up to this point. But in high school, even starting at Math 8, Math 9, I ask my students to start memorizing more, like 13 squared, 169, 14 squared, 196. Notice we have the same digits here, they're just the last two are reversed. I'm giving you some little ways that you can start to remember these because as we start solving exponential and logarithmic equations, it's good to know some powers. It will allow you to solve some things even without a calculator, but you've got to have some of these things well known. 15 squared is 225, 16 squared 256. Hey, there's a memory number. 17 squared is 289, 18 squared is 324, 19 squared is 361, and 20 squared is 400. Now 20 squared is 2 times 10 in brackets squared. Notice how the 2 squared is 4, and the 10 squared is 100, and 4 times 100 is 400. So that means you should be able to do other things very easily, like 30 squared, 900, 40 squared, 1600, and so on. So knowing your powers is some good background information. Now let's move on to the main course of this meal. Just kidding. It's not a meal. It's a lesson on understanding logarithms. So first of all, let's define what a logarithmic function is. This is a function that would take the form y equals log base c of x, where we have c is greater than 0, and c is also not equal to 1. And it's the inverse of the exponential function, y equals c to the x. So as I alluded to in the intro at the beginning, inverses are an important part in this unit. The common logarithm is when you're doing a logarithm with a base of 10. So y equals log base 10 of x. Now if I want to evaluate each of these and rewrite the resultant equation in exponential form, some of you might be looking at this and saying, logarithms, man, they're the inverse of exponential functions, and I'm much more comfortable with exponential functions. So by all means, take this equation and rewrite it as an exponential equation. Here's what you do. You do 2 to the power of something equals 32. We refer to both of these 2's as bases. So when I'm reading this off, I call it log base 2. Just like here, this 2 is the base of this power, 2 to the something. We refer to this, what's going to go in the box, as the exponent. So that means the answer to a logarithm question is an exponent, and it would be the exponent that if you raise that base to that exponent, you get this thing, that power of 2. Now, in this expression, we don't refer to 32 as the power. We refer to it as the argument of the logarithm. So now that you have it rewritten this way, do you know 2 to the what is equal to 32? What is that number that when you raise 2 to that exponent, you get 32? And you can either count up, or maybe you can refer back to your list of powers of 2 that we worked out previously. And you should remember it's 2 to the 5 that is equal to 32. And so 5 is the answer to this logarithm question. Now for part B, again, instead of trying to go directly to the answer of this, what I'm going to do is I'm going to rewrite this in exponential form and see if I can make some sense of it this way. So again, I take the base and I write that as the base of the overall power here. This answer is going to be an exponent, and the argument of the logarithm is the power of 9 that we have here. So to work this out, you should recognize that 81, of course, is 9 squared, and that the fifth root of means we've got a denominator of 5 in that exponent. So the answer is 2/5 to this question. So part C is a bit of a mystery because we've got a base missing. Now, for the purposes of this course, we are going to assume that if there's no base written, we are referring to the common logarithm, in other words, log base 10. In some higher level courses, they will actually use log and not writing a base, and they will assume that the base is different. It's actually base E. E is a special number in math. It's referred to as Euler's number or the banker's number. It's approximately 2.718. You may have heard me talk about it in class a little bit. But those are generally university level courses where they talk about log being log base E. So for this course, we're going to say log. If it's not specified what the base is, it'll be base 10. So this is what we call the common logarithm. It's base 10. So I'm going to rewrite that as an exponential equation. And so now the question is 10 to the what equals 1 million? And all we have to do is count the zeros. And you can see there are 6 zeros here, so the answer is 6. Part D, if you don't know how to get this directly, I don't blame you. It's a little bit tricky, so maybe writing it in exponential form will help you out. So 3 to the what is equal to 9 root 3. And maybe at this point you're still not totally sure. So we can change the form. We can rewrite the 9 as being the square root of 81. And now that we've got two radicals, we can multiply the radicals, and that gives us 243. Now 243 is 3 to the 5. And the square root means that the exponent is over 2. So the answer is 5 over 2. Or if you like, you can write that answer as a mixed number. You could also write it as a decimal, 2.5. That would still be exact. In any case, let's move on. Here are some basic properties of logarithms that are good to know. So log base c of 1 is 0, and that's because, again, if we take this logarithmic equation and write it in exponential form, anything to the power of 0 is equal to 1, provided that something isn't 0 itself. Log base c of c is 1 because, well, if you write it in exponential form, it also makes sense. C to the 1 is equal to c. Log base c of c to the x is equal to... Now, if you're not sure, start by writing it in exponential form as we did before, and then say, what is that exponent that we should have here so that it becomes c to the x? Oh, well, of course, this must be an x. So what we're saying here is basically that if we have a number and we do c to that number, and then we take log base c of that result, we're going to get x back. So actually, before I go on to the next result, I can just show you a numerical example of that will illustrate this property. So let's say I'm taking log base 2 of 2 cubed. All right, so the 3 here, the 3 is the input. I'm replacing x with 3, so this is kind of our start here. And when I evaluate this expression, I evaluate the 2 cubed first. So if I do 2 cubed, that's equal to 8. And now if I do log base 2 of that, I am looking for the number that is the exponent on 2, and 2 to that something will give me 8. Well, of course I know that's 3. So look at that. We ended up with a 3 again. So again, what we're saying is that if you start with a certain number, if you start with any number and you do c to that number, just like here, we started with the 3 and we did 2 to the 3, we get a certain result. And if you take that result and then you do log of the same base, so I do log base 2 of all this, log base 2 of 8, I get the 3 back. So I start with 3, doing 2 to the exponent does one thing, log base 2 undoes that, and I get the 3 back. This is what we mean by inverses. So we have the same thing but done in the opposite order here. So if we're looking for what is the result here, it would be the result because log base c of that something would be log base c of x. Well, of course, that something has to be x. So just using a numerical example to illustrate what I'm talking about here, let me just choose a different base. So I'm going to do 3 to the exponent log base 3 of 81. So in evaluating this, what I do, so again, this is my start point. This is like my x. I'm replacing x with 81, and I'm using a base, which in this expression is c, equal to 3. So if I do log base 3 of 81, I know that 3 to the 4 is 81. And so 3 to the 4 equals 81. So I get back the thing that I started with here. This is the end result. Notice those two things match. So when you start with some input like x and you do log base c of that, then you take that result and you do c to the power of that, you'll get the x back. Again, I started with 81 here. I did log base 3. That gave me 4. Then if I take that result and I do 3 to the power of that 4, I get back to 81. So log does something, the exponent undoes that. These are inverses. All right, let's take a look at what's next here. We want to determine the value of x for each of the following. So if you're looking at an equation, and if you're not sure what the answer is directly, you can always change the form, either from logarithmic to exponential or exponential back to logarithmic. So when I'm looking at this, I'm thinking, well, maybe I want to rewrite this in exponential form, right? The argument of the logarithm is the power. Here's the base. The answer to the logarithm question is the exponent. So this is 4 to the minus 2. 4 to the minus 2 is 1 over 16. And as a check, if we put the 1/16 in here and we do log base 4 of 1/16, that would give us -2. Next one we've got here, log base 16 of x is -1/4. So if I rewrite that in exponential form, then here, what I'm going to do is I'm going to evaluate this. So 16 to the negative 1/4, I'm going to go 1 over the 4th root of 16, and the 4th root of 16 is 2. So the answer is 1 over 2. Final example, and you notice that the x is in a little bit of a different place in this equation, but no worries, again, we can write this in exponential form. So x to the 2 over 3 is 9. And now if you're solving for x, you would want to raise both sides of the equation to the 3 over 2. Your laws of exponents tell you you multiply these two things and you get x to the 1. And 9 to the 3 over 2 is, well, the over 2 means you're taking the square root of 9, and that's 3. And 3 cubed is 27. So this is your final result. All right, let's do some graphing. We want to graph y equals 2 to the x and its inverse on this grid. We want to find the equation of the inverse of y equals 2 to the x and identify some key features for both graphs. So starting with y equals 2 to the x, and I'll tell you the points that I put on here. So 2 to the 0 is 1, so I've got 0, 1 on there. 2 to the 1 is 2, so I put 1, 2 on there. 2 squared is 4, so I've got 2, 4 on there. And 2 to the 3, or 2 cubed, is 8, so I've got 3, 8 on there. I also have some negative x values I've used, so 2 to the minus 1 is a half, 2 to the minus 2 is a quarter, 2 to the minus 3 is 1/8, and so on. You can see the direction that it's going, so you continue those directions and put arrows on the ends of that curve. And I can easily identify this is y equals 2 to the x, and it's got a horizontal asymptote here at y equals 0. Now to do the inverse, all we need to do is switch the x and y coordinates. So here are a few points I've started with. So notice how I took 0, 1 and put it on 1, 0. How I took 1, 2 and put it to 2, 1. 2, 4 became 4, 2, and 3, 8 became 8, 3. So I've got a bunch of points here. And similarly, I can take each one of these points, switch the x and y coordinates. So negative 1 and a half becomes a half and negative 1. Negative 2, a quarter becomes a quarter and negative 2. Negative 3 and 1/8 becomes 1/8 and negative 3, and so on. You can see the direction this is going here. And here's the equation. So you can either write it as x equals 2 to the y just by switching the x and y coordinates. But of course, this is exponential form. If I rewrite it in logarithmic form, it would be y equals log base 2 of x. So log base 2 of x is the inverse of 2 to the x, and 2 to the x is the inverse of log base 2. It also has a vertical asymptote here at x equals 0. And so now we just want to talk about a few of the key features of both graphs. So first of all, you'll notice that the domain of y equals 2 to the x is any real number. You can use any real number as input for the exponential function. And that matches the range of the inverse. Y can be any real number. You'll notice that the inverse function extends all the way to negative infinity for y values, and eventually will go up to very large positive values as well. The range of the original y equals 2 to the x is y is real, but y has to be greater than 0. Similarly, with the logarithm function, it's x greater than 0. So there's a restricted domain here. The intercepts are 0, 1 for the original function, and of course 1, 0 for the inverse. And that pretty much covers it. So again, before we get using calculators, it's good to know how to do some evaluation using your brain and even doing some estimation. So if I'm looking at this example here where it says to estimate log base 3 of 50, what I can do is identify, I know that 3 cubed is 27, and I also know that 3 to the 4 is 81. So there's got to be some number in between that will give me 50. So 3 to the something is 50. I don't know exactly what it is. You could certainly guess. The actual answer is 3.6. So I'll give you one way that you can figure out when the exponential function works out to 50. So I'm just going to bring up a calculator. All right, here we go. And so I'm going to put in y equals 3 to the x. And then here I'm going to put y equals 50. So now I'll hide those things away, and I can't really see where they cross yet, so I need to, there we go. And I can see where these two cross. There it is, 3.561. So it's approximately 3.6 that gives you log base 3 of 50. Now, you're probably looking at this and saying, but there's got to be some other way to do it, and certainly there is another way to do it. You can use a function, and I believe it's under miscellaneous. Yes, it is. So you want to use the one that's log base a. So if you put in that log base a, you have to specify your base, which is 3 here. And the mirroring is not working. There we go. So log base a, and you choose a equals 3. And now you specify the base, the argument of the logarithm, which is 50 in this case. So log base 3 of 50 will give you the same result, approximately 3.6. All right. So final example here, we're looking at how logarithms are used in Richter scale. So the Richter magnitude, m, of an earthquake is defined as log. Now notice there's no base specified. That means it's log base 10 of a over a naught, where a is the amplitude of the ground motion for the earthquake in question, and a naught is the amplitude of ground motion for a so-called standard earthquake. So what you need to know is this. Earthquakes have huge variance in their destructive nature. The ground motion, the ground shaking, can be very, very small. I remember the first time that I moved to British Columbia. I was in an apartment building, and my wife woke me up in the middle of the night. She said, "Oh my gosh, Andy, there's an earthquake." And I was literally just being jostled around in bed. And it wasn't my wife that was shaking me. It was, the bed was just moving due to this earthquake. But it was a very gentle shaking. It didn't even wake me up. It was my wife that had to wake me up to let me know there was an earthquake going on. And I said, "Oh, okay, just go back to sleep." Anyway, so that's a very small earthquake. I think it was kind of far away. It wasn't close by. On the other hand, you know that very powerful earthquakes can take down entire buildings. So there's a huge amount of variance to these earthquakes. So if you look back at this example, you notice how logarithms tends to take things that are large, like even when we get to 8 and we take log base 2 of 8, it sizes it down to 3. Now think about log base 10. If you do log base 10 of something like 100, you only get 2 as output. So the reason that log is used with earthquakes is it takes the amount of ground motion there is and sizes it down to a number that most people can have better comprehension of it. So hopefully at the end of this you'll have a little bit better understanding of the Richter scale and how it relates to the impact of earthquakes. Let's take a look at some examples here. So first thing, what is the Richter magnitude of an earthquake whose ground motion amplitude is 10 times that of a standard earthquake? So we're talking about the amount of ground motion is 10 times the standard one. So as you can see here, the A naught divides out and you're left with log of 10, which means log base 10 of 10. This gives you 1. So a 1 on the Richter scale has 10 times the ground motion of a standard earthquake. And if you have 100 times the amount of ground motion, what you'll notice is that this is a Richter scale value of 2. So every time we're going up one number on the Richter scale, it's actually 10 times the amount of ground motion, the amplitude of the ground motion. And so, like I said, because there's such a huge amount of variance between earthquakes, we use logarithms to take that crazy large amount of variance and size it down to numbers that are more manageable for us to look at. So now if we go the other way around and we say we've got, if we want to compare the amplitudes of ground motion for earthquakes that have these Richter scale values, 3.5 and 6.0, then here's what we would do. We would say, okay, so we've got one that's got ground motion that's 10 to the 6 times the standard earthquake, and we've got another one that's 10 to the 3.5 times the standard amount of ground motion for an earthquake. So what you'll notice is that the A naughts divide out, and we're left with 10 to the 6 over 10 to the 3.5, and we can use our laws of exponents to simplify this. The 6 minus 3.5 gives us 2.5. And 10 to the 2.5, if you evaluate that with a calculator, might be a little bit easier. You get approximately 316. And so what we're saying is the difference between these two earthquakes, one is 3.5, the other one is 6.0 on the Richter scale, is that the larger earthquake, the one that's more powerful, has ground motion amplitude that is about 316 times the size of the smaller one. Sorry, there was supposed to be an X in there. 316 times the size of the ground motion on the smaller one. So that concludes this lesson on the basics of logarithms, understanding logarithms. Did a little bit of application with Richter scales. Hope you understood that well. And thanks for watching. Have a great day.